take a moment to reminisce personally about the way things have developed. Back in 1999, Robin Ball and I organised a programme at this institute, at the Newton Institute, on fractal mathematics and applications. Bertrand was there, I think Peter was there for a short time, I think most of the rest of you were still at high school. Anyway, Benoit Mandelbrot was a very prominent figure at that programme, and what was then called the 4/3 conjecture about the exterior perimeter of Brownian motion was sort of discussed, and really it was felt things like that were still a long way off. But at the same time, the subject of SLE was just being born, and coming back 15 years later to the Newton Institute, it's just amazing how this subject has developed and how things that were regarded as way out of reach 15 years ago are now being talked about so freely, and it's wonderful to hear about all this development. So thank you for allowing me to come and listen to it. Anyway, our next speaker, Cédric Boutillier from Pierre and Marie Curie, Paris, is going to tell us about the Z-invariant massive Laplacian on isoradial graphs.
Thank you very much. So it's a great pleasure to be here today. I would like today to present joint work with Béatrice de Tillières and Kilian Rachel from Tours, where we construct on the family of planar isoradial graph massive Laplacian, which has a lot of nice integrability structures and that can be used to do some statistical mechanics out of criticality. So first I will start defining what is an isoradial graph, then I will talk about some results about critical statistical mechanics on isoradial graphs, and then I will say what can be done with this massive Laplacian on these graphs, and how it is defined, what are its properties, and so on. So to construct an isoradial graph, you can start from a tiling of the plane with a rhombi with the same edge length, like the one that was on Vincent Beffarat's shirt yesterday. Or you can also use this one, for example. So since so it gives me some graphs on the plane, and all the faces are quadrilateral, so it's bipartite. So I have two. I can color the vertices in two colors, such that two incident vertices are of different colors. And now, if I look, for example, at just the round white vertices, and I join them if they are at the extremities of the same rhombus, I get a new graph, which is the black one, and this graph is what is called an isoradial graph. Okay. So if instead I was taking the other family of vertices and join them with the other edges, I would have, okay, so that's the isoradial graph. And if I was taking also the other vertices and join them with the other diagonal, I would get the green graph, which is in fact the planar dual graph of this isoradial black graph. Okay, so so these are the kind of graph we will be looking at. And why are they called isoradial graphs? It's because if you look at all the faces, in fact, they can be inscribed in circles, and all these circles have the same radius. So all the faces are in circle of the same radius, which explains the name isoradial graph. Okay, so this is an example of graph we can consider. So what is nice with these graphs? Well, first, there are some transformation we can apply on the graph which preserve this property of isoradiality. The first one is that you can, in fact, tilt a little bit all the rhombi with a given direction, and so it will yield the same graph but with a different embedding. So this is exactly the same graph, but since the angles of the rhombi have changed a little bit, then the embedding of the graph has changed. We can also apply some transformation that change the topology of the graph structure. These are called star triangle transformations. So every time in my isoradial graph I see a vertex of degree 3, I can transform it by removing the center vertex here and connect together the 3 remaining vertices to get a triangle. So in the graph of rhombi, it corresponds to just rearrange the rhombi in the small hexagon that is here into the other allowed configuration. And reciprocally, if you see a triangle, you can do the reverse operation, which means that you add a vertex and you connect it to the remaining vertex. Okay, so this star triangle transformation has nice geometric interpretation. So in fact, if you think again at this graph of rhombi I had at the beginning, you can see it as a monotone surface in some hypercubic lattice in some dimension d. And doing this star triangle transformation on the graph means for this monotone surface that you add or remove a little cube in this monotone surface. And in fact, it's a theorem by Kenyon that if you have 2 monotone surfaces in that D that that coincide outside of a large ball, then you can go from one monotone surface to the other by adding these small cubes. So to reformulate this, if you have 2 isoradial graphs that coincide on a large ball, then you can transform one into the other by a sequence of such operations. Okay, so it's a nice family of operations that preserve isoradiality and can connect different isoradial graphs. So isoradial graphs are also a nice support to develop a theory of discrete analytic functions. Why is that? Because if you have a rhombus like this, and you have a function defined on the, well, so imagine you have your tilings with rhombi, and you take a function defined on the vertices of this tiling of rhombi, then there is a nice notion of discrete holomorphicity which mimics the Cauchy-Riemann equation we have in the continuous. So we say that a function is discrete holomorphic if every time I see a rhombus like this, if I compute the gradient from my function along one diagonal, it's equal to the gradient along the other diagonal. So planar graphs are also very nice to do statistical mechanics, and especially isoradial graph, because with the embedding you have using the geometry of your rhombi, you can you may want to use the geometric information you have in this rhombus to define the coupling constant of your model of statistical mechanics. So every edge of my isoradial graph was a diagonal of a rhombus like this, E. So it's naturally associated with the angle of this rhombi, theta E. And if I have a model of statistical mechanics with a coupling constant on the edges, I can decide to make them some function of these angles. And so we are looking at some particular coupling constants. So what we would like for our model is that when we do this very natural transformation on the isoradial graphs, so from the star triangle transformation, we would like that the model behave nicely. So it's a property we call Z-invariance. So we would like that if we have two graphs that differ, for example, by just one such star triangle operation, we would like the statistical models to be coupled in such a way that the configurations outside the location of the transformation are the same. Okay? So if you want to impose this on the weight, you have to write some equation that needs to be satisfied by these edge weights, and these are called the Yang-Baxter equations. So you will have some equations relating the coupling constants for these three rhombi here and the three rhombi here. You can massage them a little bit and get some functional equations that will somehow force the form of this function g of theta. So if you have on one side a theory of discrete complex analysis and statistical mechanic models, you may want to look at critical statistical and mechanical models. And one first example is some models that can be defined from the Laplacian on these isoradial graphs. So, so to define this Laplacian, I introduce some conductances on the edges of my graph. So I want them to be functions of the angle of the rhombi, and they are defined to be equal to the tangent of the angle. So I compute the Laplacian as usual as some linear combination of the gradient of the increment of the function at some vertex along the edges incident to this vertex with this coefficient given by the conductances. So the first thing that we can notice is that if I take a discrete holomorphic function in the previous sense and I just look at its restriction to the isoradial graph G, so just half of the vertices of the graph of rhombi, then it's harmonic exactly for this Laplacian. So it turned out that there is a very nice family of harmonic functions for this Laplacian, and they are defined in the following way. So you take a parameter z to be some complex number or even infinity, and you fix a base point x0 on your isoradial graph. And if I have a vertex x, I can consider some path in the graph of rhombi from x0 to x. So it's the path x0, x1, x2, etc., xn. So in this path of rhombi, all the steps are unit vectors. So ei alpha 0, ei alpha 1, and so on. And I define a function, which I call discrete exponential function from x0 to x, depending on the parameter z, to be this product. So it's a product along the path of some factor that depend on the geometry of the steps I took. So the first thing to notice is that these functions are well defined. So indeed, if I go, if I start from my vertex, I go to the next one, and I go back, the two factors I get cancel each other. And if I go around the rhombus, then all the terms cancel. So the expression that is here is in fact independent of the path I chose from x0 to x. Okay, so if instead of this rational function you prefer trigonometric function, you can just take z to be e to the iu, and it's just a product of some tangent, depending on the angle of your path of rhombi and this parameter u. Okay, and so Merca proved some nice properties of these exponential functions. So in particular, if you have a finite isoradial graphs, these are a natural basis for a natural generating family of harmonic functions. So any harmonic function can be written in a pretty explicit way as a linear combination of these functions. So if I want to look at the green function of my Laplacian, well, it's harmonic, well, except at some particular vertex, but it should be also expressed in terms of this exponential function, and it's indeed the case. So Kenyon proved that if I have an infinite isoradial graph, the green function for the Laplacian is given by this expression. So if I have two vertices x and y up to some constant, the green function is given by the integral of my discrete exponential function from x to y times the logarithm of z against some measure. So I integrate this whole thing along some complex contour that will include in its interior all the poles that could appear from this exponential function. And I have to be a bit careful with the branch cut of the logarithm I'm choosing. Okay, so a few remarks about this green function. So it's very it's a very striking fact that in fact since this expression depends just on this quantity, well, the only dependence on the x and y is in this exponential function, which depends only on a path between x and y. Then this means that the quantity I want to compute, the green function, depends only on the geometry of a path between my vertices x and y, independently of what is the structure of the graph outside this path. Moreover, it's a very nice formula, because if you have two vertices at finite distance, you can apply the residue theorem and compute exactly this integral in finite time. So it can be a bit tricky if the vertices become far away, but you can still do it. And it's also very suitable to do asymptotic analysis, because of this contour integral. You can do all sorts of expansion, and in particular, you can show that that's what also a part of the theorem by Kenyon, that the green function has an expansion that is very close to the green function of the plane. So you have this term, some constant plus some correction term, and this is completely independent of the structure of the graph we are looking at. So what kind of statistical mechanics we can look at with this Laplacian? But first, you can look at the random walk associated with these conductances, and it has very nice property already at at the microscopic level. So as in the talk by Vincent Beffarin, we can check that in fact this random walk with this particular choice of conductances is a martingale. And if we look at the scaling limit of this random walk up to time reparametrization, it will be a standard Brownian motion in the plane with a covariance metric, which is the identity. But you could do also other things like spanning trees on the isoradial graph. So, so if you have a finite graph, you can construct a Boltzmann measure on spanning trees of this graph by declaring that the probability of spanning tree is proportional to its weight, which like in the talk of Laure, is defined as the product of all the conductances of the edges present in the tree. And in fact, so using the locality property of on a finite graph, this the partition function of the spanning trees is computed through the matrix tree theorem by Kirchhoff from a principal minor of the Laplacian. And in fact, you can construct via exhaustion of your infinite isoradial graph by a finite graph a Gibbs measure on the whole on spanning trees of the whole infinite isoradial graph, and it will be a determinantal process on the set of edges of the isoradial graph, and the kernel of this determinantal process is the transfer impedance matrix, which is a linear combination of the green function at the various extremities of the edges you're considering in your kernel. And it turned out that with this choice of conductances, the measure on spanning trees is Z-invariant. So this can be checked as follows. So if I have two isoradial graphs, G and G prime, that differ just by star triangle transformation, I can check that given what happens outside a small hexagon that contains in G this star here and in G prime this little triangle, the sum of the allowed weight inside this hexagon are the same in the two cases. Are the same in the two cases, and the fact that they are the same is based on some very nice trigonometry identity, which is called the triple tangent identity. And so the conductances on the isoradial graph satisfy this quite magic formula, and it's the reason why somehow you can you have this nice property with respect to star triangle transformation for the spanning trees. Okay, we can also do other kind of models. So there is a Z-invariant edge percolation model on isoradial graphs. So it was studied in particular by Grimet and Manolescu. So again, so you do Bernoulli edge percolation on the isoradial graph, and the probability at which some given edge is open depend on the angle theta. So you can have independently on each rhombus these two configurations with probability p of theta or 1 minus p of theta, and for Z invariance to be to occur, you need p theta to be to satisfy this relation. So in particular for the square lattice, the angle theta is pi over 4, and you recover that you get 1/2 for this parameter p. So this special parameter for special choice for the percolation probability is kind also special because it satisfies some self-duality property, and in fact Rimet and Manolescu were able to prove some Rousseau-Samuel-Welch behavior for this percolation on isoradial graphs, meaning that the probability of crossing certain rectangle is bounded away from 0 and 1 uniformly. But you can also do a critical Ising model, like in the talk by Beatrice. So, well, I will not define the model. We saw it already many times. But if you want to have at the same time Z-invariant, so a nice property regarding the star triangle transformation of your isoradial graph, and a kind also of self-duality, then you have no choice. You need to choose the coupling constant of your Ising model to have this form. So again, we see some trigonometric functions. And on this model, you can do many things. So it has been studied by many people. Chelkak and Smirnov, Julien Dubeda, Beatrice and myself also have some work on this. So you can prove that this model is in fact really critical in the classical sense. You have at the discrete level a fermionic observable which satisfies some discrete holomorphic equations. The scaling limit of this model is known to be conformal invariant, but you can also construct Gibbs measure on the infinite isoradial graph, and this measure has also very nice properties. So, for example, so we construct this measure with Beatrice using a mapping with dimers, and in this context, we can see that on the infinite isoradial graph, the correlations between the spin depend only on the geometry of the embedding of the graph on paths connecting the spins, but not on the graph structure outside of this path. Okay, so that's it about critical statistical mechanics model. So what could we do about off-criticality models? So, well, first, why is it maybe interesting to look also at off-criticality models? Well, because there is some hope that you can have a parameter in this family of model that you can play with and really see the phase transition when you arrive to the critical point. And it can also allow us to study near critical systems where you can look at some scaling limits when you let the mesh of the graph go to 0 at the same time as the parameter you can play with go to the critical value. And what we would like to do is to somehow preserve the nice things the nice features of the critical model we saw before, namely the locality properties of the green function, of the spin correlation, things like that, and the relation of the coupling constants of your model with integrability, and so we want our off-criticality models to play well with the star triangle transformation of the isoradial graph. So for this, I will now construct the massive Laplacian we defined with Beatrice and Kilian Rachel. And somehow to go beyond the criticality, you need to leave the world of trigonometric function and use elliptic functions. So now the conductances I will put on my isoradial graph are defined as ratio of trigonometric elliptic functions, classical functions Cn and Sn. So you don't need really to know much about them right now. So the only thing, well, maybe. So these functions depend on an extra parameter k, which is the elliptic modulus of this function, which is between 0 and 1. And when k is equal to 0, you recover the usual trigonometric function. So Sn becomes a sine function, Cn becomes a cosine function. And when kappa equals 1, you get some hyperbolic trigonometric functions. So, and this ratio is denoted by SC, somehow the n is cancelled. And it's the elliptic generalization of the function tangent we had in the critical case. So the parameter of these functions is not really the angle of my rhombi. It's they are rescaled by some constant that that depend on this elliptic integral of first kind. So that will so that's the weight I will put in my Laplacian for two vertices that are neighbors, and on the diagonal term I will have the sum of the conductances plus an extra term that will also depend on this parameter k and is a function of the geometry of the embedding near my my vertex x. Okay, so this is the Laplacian. So I will not write the expression for the mass. It depends on other elliptic functions, but not. So it turned out that this massive harmonic Laplacian, like in the critical case, has also a very nice family of massive harmonic functions. So they are defined in a very similar way. So now, so before we had the parameter z that were living on the Riemann sphere. So now the parameter I'm using u is living on a torus tk. So which is obtained by gluing together a rectangle with say 0 for k of k and for k of k prime. And they are defined as follows. So you take a path in your graph of rhombi from x0 to x. You have these unit vectors that are the steps of this path, and you compute locally a function by collecting factors that are well, some elliptic function of the parameter alpha of which was describing the direction of your unit step. So in fact, this should be tilde. And so again, it's easy to check that these functions are well defined, and it turns out that these functions are discrete massive harmonic. So the reason why it's true is that it's because of some subtle generalization of the triple tangent identity I showed you, which is true in the elliptic case. So, well, again, these discrete massive exponential functions are very nice. They are a natural generating family for discrete massive harmonic function. So if I look at the green function of the massive Laplacian, it's again given by some generalized linear combination of these discrete massive exponential function. So now, so what we have? So we have some constant here, and we integrate this exponential function by letting the parameter u run along some contour in this torus tk. So this is tk. So my my exponential function is a product of terms. So these functions SC here are in fact some meromorphic functions. So they have some poles on the real locus of this tori. So you have an horizontal contour here with some poles along this term that correspond to the poles of the exponential function between x and y, and the contour gamma. So these poles are in fact in just 1/2 of this horizontal circle, and the contour gamma is somewhere in the other half. So it doesn't really depend where it's located, because we deal with holomorphic function in this neighborhood, but we have a very nice description of this. So this really mimics the structure we had in the critical case. And so what can we do with this? Well, first we can compute what happens on the diagonal. So this term corresponds to the expected time of the continuous random walk with the conductances I presented before on the graph, with some killing rate, and it turns out that this expected time, in fact, it's just a function of this parameter k, and it doesn't depend on the geometry of the graph. It's just some universal constant. And when k goes to 0, so we are going to the critical case, this quantity goes to infinity. And in fact, if we subtract this quantity to the green function and let k goes to 0, we recover the formula for the green function that Kenyon gave for the conductances given by tangent. Using the knife integral representation, we can do some saddle point analysis and compute the explicit exponential decay of this green function. So it's unfortunate. It's not isotropic, so it really depends on the direction in which x and y are followed.
It's not exponential minus mx?
No. No. Yeah. So at finite k, so if k is strictly positive, you get something that is not rotationally invariant. But if you do some joint scaling where the points are going far away at the same time as k goes to 0, then you get something that becomes isotropic at the end. Okay, so what kind of statistical mechanics you can do with that? Well, it turned out that if you have a massive Laplacian, then it's determined on a finite graph. Its determinant counts no more the spanning trees, but spanning forests. So what are these spanning forests? Well, it's just collection of trees that pass through all the vertices, and these trees are rooted at some vertex. So each connected component of this graph has exactly one root, and the connected component can be reduced to one point. And they have a natural weight associated to them. So if I have a forest, the weight of the forest is the product over all the rooted trees. So T is the tree, xt is the rooted vertex. So I get the product of all the conductances of the edges appearing in this configuration, and I have an extra weight coming from the roots, and this weight is given by this mass, the difference between the diagonal term of my Laplacian and the sum of the conductances. And it turned out that these particular weights, if I take the conductances defined by this generalization of the tangent function, the mass here satisfies the Yang-Baxter equation. So it's a quite long computation. There's a lot of case to deal with, because now of the more intricate structure of this spanning forest. But so it's another motivation for this particular expression of the conductances. And again, by looking at exhaustion of my isoradial graph by finite graphs, I can construct a measure on spanning forests on the infinite isoradial graphs. And again, this spanning forest will be a determinantal process on edges, and the kernel will be the transfer impedance matrix associated with this massive green function. So having an explicit expression for the green function allows us to compute exactly many things about this spanning model. So there is some more magic about these conductances. So what happens is, if now I suppose that my isoradial graph is periodic, so it is now made of a fundamental domain that is repeated periodically in two directions. And if I look at my massive Laplacian, it's a periodic operator on this infinite graph, and I can compute its Fourier transform. So I denote this by Laplacian hat. So it's just a finite matrix with rows and columns indexed by the vertices of a fundamental domain of my graph, and it depends on some extra parameters z and w that are the conjugated quantities to the translation of my graph. So you can just think of them as extra weight on edges that are sticking out of the fundamental domain of my graph. So I have a finite matrix with parameters z and w, and I can compute the determinant of this finite matrix, and it gives me a polynomial. And if I look at the zeros of the polynomials, well, it turns out that this algebraic curve encodes a lot of information about the model, and with the particular weights we put on edges, the geometry of this curve is also very specific. So what we can prove is that every time we take a value of k that is strictly positive, the algebraic curve we get is a genus 1 curve. So it's a torus, and it has some symmetry when you replace at the same time z and w by z minus 1, w minus 1. So this symmetry is comes from the fact that the Laplacian is a symmetric operator. But the striking fact is that it's always a genus 1 curve. And we have an explicit parametrization of this curve by the small torus tk. So what are the two parameters? So if I take u in my torus, then the solution, the zeros of my curve can be parameterized by z of u and w of u that are computed as the massive exponential function between x and its copy in the neighboring fundamental domain. So if you have x here and x plus the horizontal translation, and here x plus the vertical translation. So if you look at in the graph of rhombi a path between this point and this point, and you compute the massive exponential function, you will get exactly a parametrization of the curve. So the curve C so looks something like this. So this corresponds to point at infinity. So it can have singularities. So it will have, in general, have some singularities, but it's a torus, so it has only one handle, and we have a very nice parametrization by this very nice torus using these discrete massive harmonic functions. So on the periodic graph, using this curve, and also using deformations of the isoradial embedding, we can compute the free energy per fundamental domain of the spanning forest. And it's interesting to look at what happens when k goes to 0. So when you approach this, the case of the spanning tree. So when the parameter k goes to 0, the measure on the spanning forest converges to measure on spanning trees of the isoradial graph. And if you look at how the free energy behaves when you approach the critical point, well, you get so this is the value of the free energy for spanning trees computed by Kenyon, and the corrective term is k squared log k. So it's a second order phase transition. Why this massive Laplacian is also important in other contexts? Well, so if for So we defined before the critical Ising model on isoradial graph. So with specific parameters that were trigonometric function, because of the fact that we implied we forced the model to be Z-invariant and to have some self-duality property. But if you remove the constraint of self-dual property, you get this expression that was found by Baxter. So again, the coupling constant for a general Z-invariant Ising model is given by some elliptic functions. And it turned out that the Ising model can be studied through a correspondence with a Daimer model, with one of the bijections that Beatrice showed you during her talk. And the Daimer model has a spectral curve, which is computed a bit as I did before, but not for the Laplacian, but for the Castellane matrix. And it turns out that if you look at the specific Daimer model for which corresponds to the non-critical Z-invariant Ising model, the spectral curve is exactly the same as for the massive Laplacian. So these spectral curves, in fact, dictate somehow in the case of periodic graphs, you can really read the exponent of decay of the green function on the geometry of this curve, and the fact that this curve is the same for the massive Laplacian and the Ising model tells you that the decay of correlations of the spins in this model should be related to the decay of the green function in the massive case. Okay, so that's it for the talk. Just before the end, I would like to show also some animation. So I would like to show you how we can see the phase transition in the Ising model using the spectral curve. So I will show you the evolution of the spectral curve when I let the parameter k go to 0. So in fact, I will show you the movie in the other side. So we will start from criticality and go away out of criticality. So what I will display is what is called the amoeba of the curve. Okay. So these curves live in C2. So it's it's a surface in a 4-dimensional space. So it's not very easy to show on the screen, but you can somehow project it by just looking at the modulus of the points of this curve. So I will map it to what is called the amoeba. Okay. Okay, so this is the starting point when k is equal to 0. So this corresponds to the critical Ising model or the critical Laplacian, and so we know from result by Kenyon, Okunkov, and Sheffield, and Kenyon, Okunkov, that the corresponding curve has this shape, and it has no hole at the moment. So there is a very singular point at the origin that for the moment we do not see. So this corresponds to the spectral curve of the Ising model on the hexagonal lattice with a fundamental domain of size 4. Okay. And now I will increase so it's the critical case, and I will increase the temperature. So as K increases, you see this hole appearing, and so it's growing with the temperature, or with with this parameter K, which also controls how the mass is growing in the Laplacian, and K is approaching 1 and up.
Is there any importance that the fundamental domain is a square of what you are doing?
Well, it's not really a square. I drew it a square, but
yeah, so that's the question. I mean,
no. So it's just some pattern that is repeated.
Miles? Yeah.
Two naive questions. One is that can you have some monotone coupling as K is in between the forests, or not? But
that would be very nice, but so I don't really know how to do it. So for fixed K, you can say that you can generate this forest using Wilson's algorithm, but when K is increasing, somehow you are increasing the killing rate of your random walk, and so it's not clear that the scenario that can occur when you are erasing the loops are somehow consistent with the changing K.
but is it at least true that all the conductances are monotone?
Yes, and it's also true that if you look at the mass divided by the conductances is increasing.
Yeah, well, transition probabilities.
Yeah.
and if you have this theta build-up, looks like you introduce some curvature. I don't know. You change the angles.
Yes.
So is there some, you introduced mass, so it changed the curvature? Is that a realistic? I mean, is there some physics wisdom how your mass is changing your curvature?
Yeah, maybe. Well, so it's not very clear what is the right picture, but because somehow you need both settings. The graph of rhombi, where you have all these parallel edges. So here you really, so to be able to transport, to construct these exponential functions and to have the angles well defined in the whole graph. And on the other side, it would be more natural to have these angles that do not sum to 2 pi, but to k. And which would in fact indeed correspond to some curvature at vertices.
Could it be that the explanation is that that you look at basically a one-dimensional Brownian motion living on the edges, and that somehow you can interpret your M as just the killing rate of this continuous time guy that you just see the ghost of while looking at what happens on the sides? and that somehow would explain the Sn, Cn, and the relation with the m and so on. That sort of would be the expected time.
Well, so this elliptic function would appear naturally if you look at.
Yeah, this is my question. Maybe no.
Will you say again? To look on what?
I mean, it's a bit like a Tito's train track thing. So that you would say basically you would have a real Brownian motion living on the edges,
Sure.
and that somehow the
The trace on the visited vertices.
and this one would just have a killing rate and.
Yeah, so we were just looking at the random walk with discrete steps, but in continuous time. But
Exactly.
maybe
So then you are basically waiting by something involving the expected times of.
could be. Yes.
Okay, well, can we thank all this morning's speakers once again? I think Nathaniel has an announcement.
Yes, so